Hello everyone, welcome to the 15th video of our lecture series. So let us move to the first problem of today's lecture. So we have a particle of mass m in a potential which is given. So we have to find the change in the ground state energy compared to the simple harmonic oscillator potential to first order in G. So we know that the simple harmonic oscillator Hamiltonian is p squared by 2m plus half m omega squared x squared, and for this potential we know ground state energy E0 is half h cut omega. Now we have the Hamiltonian p squared by 2m and potential energy is half m omega squared x squared plus we have g cos kx. So we can write this as h harmonic, this is harmonic oscillator potential plus an extra term. So this we can treat this as perturbation. So we are perturbing our simple harmonic oscillator Hamiltonian with the perturbation term this, and due to this we have to find the correction to the energy in first order in G. So that means we have to use here first order perturbation theory. So we know that in first order perturbation theory, suppose so if ground state wave function is phi 0x, then the first order correction E0 in ground state, that means ground state energy first order correction will be minus infinity to infinity psi 0 star x h dashed psi 0 x dx. Now we know that for a harmonic oscillator the ground state wave function is given by m omega by pi h cut whole to the power 1 by 4 e to the power minus m omega x squared by 2h cut. So this is our ground state wave function of harmonic oscillator in position basis. So we have to evaluate this integral with psi 0 given as this. So let us proceed. So E01 we can write this as m omega by pi h cut to the power half, and here we have minus infinity to infinity e to the power minus m omega x square by 2h cut, and what is the h dashed? H dashed is g cos kx. So we are taking g outside. Here we have cos kx, and here we have again e to the power minus m omega x square by 2h cut square. So we can just multiply these two and we can write this as e to the power minus m omega x square by h cut. So this integration we have to find out. So let us proceed. So let us denote this by I. So I is minus infinity to infinity e to the power minus m omega x square by h cut into cos kx. Now we know that cos A can be written as e to the power A plus e to the power IA e to the power minus IA by 2. So this is our cosine function in terms of exponential. So cos kx can be written as e to the power ikx plus e to the power minus ikx by 2 dx. So we have a summation of two terms, I1 plus I2. So half, we can write this as I1 plus I2. So what is our I1? I1 is minus infinity to infinity e to the power minus m omega x square by h cut into e to the power I k x dx. So we will now try to expand this in this term as e to the power alpha x or ax plus b whole square. So how we will do that? So let us proceed. So we have here minus infinity to infinity e to the power minus m omega x square by h cut minus ikx dx. So now if we denote this as p, so p is our m omega x square by h cut minus ikx. So we can write this as root under m omega by h cut into x squared minus 2 root under m omega by h cut x, but we have to have here ikx. So what we will do? We will multiply this with ik by 2 into h by m omega. So this is this term and this term will cancel out and 2 will cancel out. So we have ikx. So now, but this can be written as a square minus 2ab. So we can write this as b squared. So we have added this extra term here, so we have to subtract this. So ik by 2 root under h cut by m omega squared. So this can be expressed as root under m omega by h cut x minus ik by 2 h cut by m omega squared minus I squared will be minus 1. So we have plus 1 h cut k square by 4 m omega. So from here also we can take this term common, m omega by h cut root under. So this root will be squared and we have x minus I k h cut by 2 m omega squared, and here we have h cut k squared by 4 m omega. So this is our p. So now we can write I1 as minus infinity to infinity e to the power m omega by h cut x minus I k h cut by 2 m omega squared plus h cut k squared by 4 m omega d omega. So we can take out this term. So e to the power h cut k squared by 4 m omega, and here we have minus infinity to infinity e to the power m omega by h cut x minus I k h cut by 2 m omega squared, and here we have so this is dx. So here we have dx. So this is our I1, and so what will be our in energy correction for the first term? So energy correction from the for the first term is g by 2, and here we have m omega by pi h cut. So g by 2 into m omega by pi h cut to the power half, and here we have e to the power h cut k squared by 4m omega, and we have an integration from minus infinity to infinity e to the power m omega by h cut x minus I k h cut by 2m omega squared dx. So this integration, if we do the integration and do the calculation, so let us do this. So for this integral, if we replace this x minus I k h cut by 2m omega, we can replace this as u, so dx will be du, and integration limit will not change because this is from minus infinity to infinity. So if you add or subtract any term with infinity, so it will remain infinity. So this, from here we will get minus infinity to infinity e to the power am omega by h cut, and here we have u squared du. So and we know, we know a formula. Okay, so basically we have a minus here. So this minus we have I have forgotten to include. So that minus means here will be a minus, and this, all of this will be a minus. So this is minus, and here we will also have this minus. So it will be and yeah, now this is fine. So we know of a formula that e to the power minus infinity to infinity e to the power minus ax square dx will give us root under pi by a. So this will give us root under pi by m omega h cut. So this term will give us this. So the correction will be g by 2 m omega by pi h cut half e to the power minus h cut k square by 4 m omega, and we have here pi h cut by m omega half. So these two terms will cancel out, and what we are left with, we are left with g by 2 e to the power minus h cut k squared by 4m omega. So similarly, if we do the calculation for the second term also, that I2 term in the same manner, then we will get g by 2. You can do this easily, like the trick is like the same. So there we will have plus here, and do this plus minus sign. If you do the calculation carefully, then following the similar procedure and similar formula using, we will get g by 2 e to the power h cut k square by 4m omega. So what is the correction term in energy? So correction term is the summation of these two integral. So this is g by 2 e to the power minus h cut k square by 4m omega, and we have e to the power h cut k square by 4m omega. So this will be minus. So that means it will be g e to the power minus h cut k squared by 4m omega. So this is our correction term in the energy of the harmonic oscillator potential. If we perturb that with a potential of the form g cos kx, so our correct option is here D. Now let us move to the second problem. So we have a particle which is moving under the influence of a potential k r square by 2, and it has a wave function psi rt. Now suppose that the wave function changes to psi alpha RT. So what will be the ratio of the average final kinetic energy to the initial kinetic energy? So average kinetic energy means expectation value of kinetic energy. And we know how to calculate the expectation value of any operator. So if kinetic energy is represented by T operator, then the expectation value of it will be psi RT T psi RT, and since this is in 3 dimension, it is given by R square, so we have R square dr here. So this is our average kinetic energy. Now T we know is P squared by 2m, and in 3 dimension it can be represented in position basis as minus h cut square by 2m grad square. So what will be the expectation value? So T will be, so this is complex conjugate. So we have R integration limit from 0 to infinity psi star RT. Here we have minus h cut square by 2m grad square psi, and we have R square dr. So this is our average kinetic energy. Now suppose that psi RT it changed to psi alpha RT. So let us denote this alpha R by U. So now what will be dr? Dr will be 1 by alpha du, and what will be the grad square operator? So basically since alpha r equal to u, we can write that grad square in radial coordinate can be represented as alpha square into grad square in u coordinate. So our new kinetic energy or final kinetic energy after we change to this form will be, this limit is from 0 to infinity, psi r we change to alpha r t, and we have here h cut square by 2m grad square psi, and psi is limit is from alpha r t, and here we have r square dr. So this will be our final kinetic energy. Now we can replace this dr by 1 by alpha and r. So basically we have here 1 by alpha cube, and due to this del square we have alpha squared. So alpha squared. So 0 to infinity psi star u t. Here we have from minus h cut square 2m grad square in u coordinate, and we have here psi u t, and here we have u square du. So now notice that here u is a integration variable, so we can change u to any other symbol. So let us replace u by r. So we have psi star RT minus h cut square by 2m grad square r psi RT r square dr. But now we know that this is our initial kinetic energy. So we have our final kinetic energy, or you can write it as TF as T final will be T initial by alpha. So the ratio of the average final kinetic energy to the initial kinetic energy will be 1 by alpha. So that means ratio of average final kinetic energy by average initial kinetic energy. So this ratio we find it to be 1 by alpha. So this is our correct answer. Now let us move to the third problem. So this is the so problem states that Sx denotes the spin operator, which is defined by this. So this is a spin half Hamiltonian spin half particle Sx operator. So we have to find out the which of the following is correct. So first option is that the eigenstates of the spin operator Sx are 1 0 0 1, and second option state another possible set of eigenstate, and third option is stating that in the spin state, if this is our state of the system, then if we measure Sx, then the probability for obtaining chi x, so this is one of the eigenfunction, is 1/4, and another one is stating that if the particle is in the same state and if we measure Sx, then what is the probability for obtaining this. So we have the probability of obtaining the spin up condition. We have these two, and we have these two options for eigenstate. So let us even we want to solve this, first we have to find the eigenstate of this Sx, because we know that if this is our given state, we can expand this or as a linear combination of this eigenstates of Sx. So if Sx has eigenstate this and this, then we can represent any state or any any state, suppose psi. So we can represent psi as a linear combination of this. So we can also represent this state as linear combination of eigenstate of y. So the coefficients will obviously be different, and also we can represent this in eigenstates of z. So that is the meaning of basis. Like if so, that we know in 1D, 2D, or 3D. In 3D we have I, J, K basis, and we can represent any vector as a linear combination of these three. So similarly here, if Sx has eigenstate these two, so we assume that they are complete and orthonormal. So then we can represent any state as a linear combination of these two. So we have to find the probability for obtaining this. That means we have to find alpha squared. So let us find out the eigenstates first. So Sx we have h cut by 2 0 1 1 0. Just cross check it. So this is our Sx. So now we first to find the eigenstates, first we have to find its eigenvalue. So what will be the eigenvalue? So h cut by 2, so minus lambda, h cut by 2, h cut by 2 minus lambda. So if lambda is the eigenvalue, then it will satisfy this equation. So from here we have lambda square minus h cut by 2 squared. So our eigenvalue is plus minus h cut by 2. So if we measure Sx, we will either get h cut by 2 or minus h cut by 2. So now what is the eigenstate? So for lambda, first calculate for lambda h cut by 2. So for lambda h cut by 2 we have 0, h cut by 2, h cut by 2 0. So if AB is our eigenstate, then we have h cut by 2 AB. So we are getting h cut by 2 B equal to h cut by 2 A. So our A and B, they are same. And also we know that the eigenstates need to be normalized. That means we must have A squared mod value plus B squared mod value to be 1. So A and B, we can take its value to be 1 by root 2. So our one of our eigenstate is 1 by root 2 and 1 by root 2. So let us find out another set of eigenvalue for lambda minus h squared by 2. So for lambda minus h squared by 2, we have here 0, h squared by 2, h squared by 2, and ab, and here we have minus h squared by 2, ab. So from here we are getting the relation b equal to minus a. And again, as we have done before, the normalization condition, if we apply the normalization condition, then we will find out a and b value to be 1 by root 2. So our second eigenstate is 1 by root 2 minus 1 by root 2. So this is our two eigenstate. So so one we are calling as 1 by root 2, 1 by root 2, and we have down state as 1 by root 2 minus 1 by root 2. So let us check options. So this is not correct, and this is 1 by root 2. So up state is not 1 minus 1. So, and here both are given as up state. So like there may be a printing mistake, but this is the concept. Like in this way you can find the eigen states of any operator. Now we are given the spin state this. So if we consider this as psi, so psi is given as half 1, and here we have root 3. So we can expand this psi in terms of up spin and in terms of down spin. So now we have to calculate the probability that if we measure Sx, then what is the probability of getting this psi x? So what will be the probability? So first we have to find alpha. To do this, we have to just multiply with this. So psi x and psi. So psi x we have to be 1 by root 2, 1 by root 2, and here we have half root 3 by 2. So what is alpha? So alpha is 1 by 2 root 2 plus root 3 by 2 root 2. So we are getting 1 plus root 3 by 2 root 2. So we have to find the probability. So probability means we have to find alpha squared. That means 1 plus root 3 squared by 4 into 2. So if we simplify this, we will get 1 plus 3 plus 2 root 3 by 8. So we can, so this will be 2 plus root 3 by 4. So let us check the our options. So this is. So that is the probability that if we have this spin state and we measure Sx, then we will get up spin with probability this. And what will be the probability of getting this state? So the probability of getting this state will be 1 minus 2 plus root 3 by 4. So it will be 2 minus root 3 by 4. So this is our correct answer. So welcome to the last problem of today's video. So this problem is from atomic physics, but we have to use our quantum. So atomic physics is basically in quantum level, so we have to apply quantum mechanics. So it states that we have the spin orbit interaction in an atom, which is given by this Hamiltonian. So L and S, they denote the orbital angular momentum and spin angular momentum of the electron. So we have to find the splitting between the levels 2p3 by 2 and 2p half. So we know that these are term factors. So how term factors are represent? They are represent as 2s plus 1 L value, and here we have J value. So first let us calculate L, S and J value for 2p 3 by 2. So for 2p 3 by 2 we have 2s plus 1 equal to 2. So S we have to be half, and we know that if this is represented by P, then L value is 1, and like S, for S, if here we have S, then we have L value 0, and SPDF in the similar manner you can calculate the L value. So for D state we have L value to be 2, and and J value is here 3 by 2. So for 2p 3 by 2 we have S value to be half, L value to be 1, and J value to be 3 by 2. Now let us calculate this for 2p half. So for 2p half, so since this is same, so S value will be same, L value will also be same, and we have J value here half. So we have the S, L and J value for both the states. So our Hamiltonian is alpha L dot S. Now from the addition of angular momentum, so we know that the total angular momentum J, it can be represented as the addition of orbital angular momentum and spin angular momentum. So we have total angular momentum L, J equal to L plus S. So we know that J, L, S and MJ, like these operators, and so if we want to write this in operator form, so J, Z, they are simultaneously diagonalizable. So we will try to express this Hamiltonian in terms of these operators. So let us do. So J is L plus S. So J square will be L square plus S square plus 2 into L dot S. So why we are writing L dot S? Because L and S belong to different subspace. So L dot S plus S dot L. So here this order doesn't matter because they belong to different subspace and they commute. If that doesn't commute, then we have to take care of this order. So here we can write L dot S as half J square minus L square minus S square. So our Hamiltonian is alpha by 2 J square minus L square minus S square. So this is our Hamiltonian. So since they all are simultaneously diagonalizable, so we will take our eigenstate to be that state which is so we will take our state which is eigenstate of these three. So what is this? So the eigenstate will be J, MJ, and we have LS values. So for let us do this calculation for 2p 3 by 2 first. So for 2p 3 by 2, our J value is 3 by 2 and MJ value doesn't matter because as we have seen in the previous video that the eigen values of these operators, that doesn't depend on MJ. So we are for all the MJs the eigen value is same. So we are just writing this as MJ, and we have L value to be 1 and S value to be half. So for this state, what will be the energy? So energy will be, so if we denote this by state by beta, let us denote this by beta. So beta H beta. So it will be alpha by 2 beta. H we have j square minus L square minus S square beta. So we have alpha by 2, and what is the eigenvalue of j square? It is j into j plus 1. L value is 1, so L into L plus 1, and S value is half. Half into half plus 1, and we have h cut square. So we are getting alpha by 2, and here we have 3 by 2 into 5 by 2, that means 15 by 4 minus 2 minus 3 by 4. So these two terms will give us for 12 by 4, so 3 minus 2, that means it will have the value alpha by 2 h cut square. So for 2p 3 by 2 we get the energy value to be alpha by 2 h cut square for the given Hamiltonian. And now let us calculate this for 2p half. So for 2p half, and let us denote the eigenstate by gamma. So it will be j value is half, and we have mj, and L and S both are same as the previous one. So here we have the expectation value of energy. So this, so expectation value or average value of energy is gamma h gamma. So alpha by 2 gamma j square minus L square minus S square gamma. So we have, so what is j value? So j value is half. So half into half plus 1 minus 1 into 1 plus 1 minus half into half plus 1, and h cut square. So these two terms cancels out, and we have minus alpha h cut square. So this is our energy for this 2p half. So we have to calculate the splitting between these two levels. So what will be the splitting? The splitting will be the difference of these two energy level. So the splitting between levels 2p 3 by 2 and 2p half for given Hamiltonian alpha L dot S is, so what is the splitting? The splitting is, first we have alpha by 2 h cut square minus alpha h cut square. So splitting means the difference between them. So we have 3 by 2 alpha h cut square. So our correct option is A. So that is how, like, you can give like another states. So for every state you can calculate the corresponding J, L and S value from the term factor, and for this type of given Hamiltonian, or you can be given the only angular momentum of 2 electron or this. So it is just basically you have to apply the addition of angular momentum, and you have to find the basis which is simultaneously diagonalizable with the operators. So in that way you can calculate this types of problem. Okay, so that is it for today's video. So we will meet on our next lecture video.